We investigate the best approaches to re-jam in fluidic jamming actuators that have leaks caused by use or damage. The first approach is to continuously apply vacuum, which consumes a large amount of power. The actuator can also be jammed only once, which conserves power, but will return it to its compliant state if a leak exists. The actuator can also be periodically re-jammed or jammed once the pressure falls below a specified range. We test these approaches in a soft, 3-fingered gripper with Leaky layer jamming actuators embedded in each finger. Continuous application in vacuum maintains a high pressure and permits holding a full metal water bottle. With only a single jamming cycle, the actuator pressure decreases over time. After an average of 160 seconds, the pressure and stiffness are too low and the gripper drops the bottle. With periodic rejamming, set here to 24 seconds, the pressure is increased and the gripper is able to hold the bottle. This maintains grip performance over the entire test and consumes approximately 6 times less power. Hysteresis-based rejamming uses an onboard pressure sensor to determine when the actuator pressure has fallen out of range and rejams until the pressure hits the top of the range. The effect and performance are similar to the periodic rejamming, but in this test, the power consumption is 7.5 times lower than continuous jamming. To determine whether this approach works in other jamming systems, we also tested the single hysteresis and periodic rejamming in a robotic elbow sleeve with a layer jamming actuator integrated to support the elbow joint. We tested a slow leaking and a fast leaking actuator. The hysteresis approach yielded a lower pressure with the fast leaking actuator and lower power compared to the periodic approach. Further study in power efficiency will be a critical step to move fluidic jamming actuators from the lab and into the world.